All right, gang. So I want to talk a little bit more about the idea of collision theory that we talked about at the beginning of our kinetics module or chapter, and think about how that affects how a chemical reaction goes forward or is activated. And we're actually going to come back to this example that we looked at for equilibrium, this reaction of cis-2-butene undergoing isomerization to produce trans-2-butene. And you can see the reaction here. It's really no different from the slide essentially that we saw before with the same reaction on, but we're just going to look at it now in the kinetic sense. Now that we've looked at it in an equilibrium terms. And so the way that this reaction will proceed is first of all, we've done this before. We've seen a plot like this before, although you might say, you know what, I've not seen anything like this. But you see the initial state and the final state. So whenever we're talking about the idea of enthalpy, and where enthalpy was essentially the energy or the heat change between, products and reactants, and, those products and reactants could have different energy, be at different energy levels. And the difference between them was essentially the enthalpy. What we're looking at here is probably more analogous to free energy, and we're looking at a free energy difference. And we're going from a high free energy to a low free energy, so our change, our delta free energy, our change in free energy, or delta G, would be negative. So we'd predict that this reaction would occur, but essentially if you start with this trans or cis-2-butene and you want to end up with trans-2-butene, if you start off with the cis, it's not just going to make the trans. It may well do that, but it has to undergo or go through a number of chemical processes to make that happen. And in particular, what I mean is, in the middle of this plot, you'll see this great big energy hill. All right, and that energy hill has a certain height, and that height's going to correspond to what we're going to call the activation energy. Essentially the amount of energy that it takes to kickstart the reaction or to get it moving. Sort of like, you remember we talk about the idea of a ball sitting on top of a hill, and the ball will want to roll down the hill, but essentially if you have a ball and it's sitting right on top of the hill, it's probably not going to go anywhere until you give it a little bit of a push. That push is to overcome the friction of that ball that's impeding that ball's motion, to overcome the inertia. And you need that little bit of energy to make that ball roll down the hill. Chemical reactions are the same way, although there are some reactions where the activation energy is very, very high, and it would be hard to overcome, and so the reaction doesn't really happen because there's not enough energy to make it happen. That's what that energy is. Sometimes we'll call it an energy barrier, and we'll say the reaction has to get over the energy barrier. It needs enough energy to get to that place. But essentially, what's happening is that molecule has to get into just the right conformation, just the right geometry, in order for the process, this isomerization process, to occur. And that happens with anything, any reaction that we're talking about. There will be a state that's intermediate to the reactants and the products where everything is just aligned, and you have to get to that point where everything is aligned properly and there is enough energy to make that reaction go. We call that state the transition state. Sometimes you'll also hear it called the activated complex, where you just get to that point where everything's in perfect alignment, they have enough energy, and it's just essentially now the ball rolling down the hill to produce the products. And if you think about it, that really fits with the way that we've talked about the idea of kinetics and collision theory to this point, where, remember when we said we were talking about collision theory and we said, okay, the molecules must collide and they must be in the proper orientation. So if we want to make these two molecules, all right, there are a number of different collisions that can occur, but essentially only some of them are going to be productive. And so we said the ones where the two red atoms would collide in close proximity to one another, we might expect there to be a reaction at that point. All right, because those two, as a product, those two red atoms have to be attached to one another. So the collision has to occur that will make those two red atoms collide or get very close to one another so that they could then form some type of a bond. And we said there are a number of different non-efficient collisions. So if the red atom end of that molecule collides with the green atom end of another molecule, that's not productive for the products that we're anticipating producing in this particular reaction. That's ineffective. All right. And so we said, the more collisions that we have, the more likely it is that we'll have more effective collisions. And if we have more effective collisions, it's more likely we're going to get the product. So more collisions are going to lead to more product. It's going to lead to a faster reaction. Now, it turns out that's not the only thing that we have to consider. It's not just the orientation. It's the orientation, and there has to be high enough energy of a collision. And if you hear that, you almost would start to think, oh my gosh, the things have to collide in just the right way, and they have to have enough energy, and if they don't, the reaction doesn't occur. You might think that chemical reactions wouldn't occur at all. And that probably would give you an appreciation for how many collisions are actually occurring between molecules at any one time. It's just an enormous amount of collisions in order to get to the point where we get the correct orientation and we get the correct amount of energy to get over that energy barrier, that activation energy barrier. And so you might start to think about, okay, how do we make reactions go faster? Well, you do a reaction, you generally will heat it. All right. Why do you heat the reaction? Well, you probably want those collisions to have enough energy to get over that activation energy barrier. Okay. And not only that, but molecules move more quickly whenever they're heated. They have more energy, and so they're more likely you're going to get more collisions. So, you start to think about, okay, why do you stir a reaction? You stir a reaction because you want to get those molecules colliding with one another. And so all these little things that we do, you might say, okay, well, you just do them because you do them, but no, you do them because you want reactions to happen fast. And so I really find that really an interesting thing. And now, when we talk about this activation energy, the activation energy has nothing to do with the enthalpy change or the entropy change or the free energy change. Those things all stay the same. This kinetic stuff is completely separate. It's something that we have to consider in addition to thermodynamics when we're trying to predict whether a reaction will occur and how fast they might occur. So, for instance, if we go back here, the difference in energy between the initial and the final state stays the same no matter what the height of that activation energy will be. So this is sort of energy that's sort of outside that thermodynamics discussion that we had before, but it's energy that we have to overcome nonetheless. We have to get those molecules into the place where they're forming that activated complex, where they're at that transition state, so that we can get them to then roll off the hill and get to the product position. So, whether we have a very exothermic reaction or an endothermic reaction, or, delta G is positive or negative, it doesn't really matter if we can't get over the activation barrier. Which is interesting because remember we said that, oxidation by oxygen is very favorable. It'll have a very negative delta G, negative free energy change. It'll be very exothermic. Very likely it would be favorable entropically as well. The entropy likely would increase by undergoing that particular oxidation reaction, because you're producing water and carbon dioxide, two gaseous materials. And so we said, diamonds just don't burn up in the atmosphere, though. And why don't they? Because the activation energy is so flippin' high. You've got to have a lot of energy that goes into to get to the transition state, requires so much energy that you actually literally would have to start the diamond on fire in order to make it go. And so that's the same with us. I mean, we're sitting here in this oxygen atmosphere, and we breathe it, and we have to have the stuff, but, it wants to oxidize us. I mean, trust me, thermodynamically, it wants to oxidize us, but it can't because the activation energy is so high. So there's this balance between thermodynamic favorability and kinetics that we really have to think about and we have to worry about. All right, so now to study that activation process, or that activation energy, we're going to use something called the Arrhenius equation. All right, and I'm going to move myself over here. And that Arrhenius equation, I'll put myself right on the slide. That Arrhenius equation is going to give us factors that are going to relate to the magnitude of the rate constant. To this point, we've not talked a lot about rate constant other than if it's large, the reaction's fast. If it's small, the reaction's slow. We talked about how you might be able to calculate it from the method of initial rates. We saw how we could calculate it from the integrated rate expressions, rate law expressions. But here we're actually relating it to some physical properties. So the rate constant is equal to this factor A, which we're going to call the frequency factor. That's where the collision theory part of this comes in. It's going to account for the orientation of collisions, what percentage or what fraction of collisions are going to give us the appropriate orientation of the molecules to make the reaction go, as well as it's going to factor in the number of collisions that would occur. And so really that frequency factor has two different parts to it. It's got the orientation part and it's got the number of collisions part. And we're not going to talk about anything more essentially than A and understanding conceptually that it has those two components, but those two components are there. And then E sub A is the activation energy for the chemical reaction. And so as you can see, as that activation energy gets larger, that rate constant will get smaller. So now we're starting to see, so with oxygen and the diamond, all right, the rate constant must be exceedingly low at normal room temperature. Okay, and for that to occur, the activation energy must be very, very high. So if we can overcome that activation energy, we could burn that diamond. And we talked about how, I think we talked about how the members of my research group actually did that with a test set of diamonds that they were borrowing from someone. Now, luckily, it was like a 10 micron spot or something on the diamond, so it wasn't that big of a deal, but they were providing enough energy, but the way they were providing the energy was in the form of light with a laser. So they were focusing a laser down on the diamond. And so you have those terms. You've got a temperature term there. All right. So the higher the temperature, all right, the larger the temperature, the larger the rate constant will be. So now you might understand, okay, that's why we must heat a chemical reaction. Well, when you heat it, you're making the rate constant increase. All right. So as temperature increases, the rate constant increases, and as rate constant increases, the reaction rate will increase. So if we heat a chemical reaction, the reaction rate will increase. All right. Doesn't have anything to do with thermodynamics. All right. And I know we talked in equilibrium about how, you can make products or reactants shift around depending on what the temperature would be. That's absolutely right. But in general, rate constants increase with temperature. And that means that reaction rates increase with temperature. So we would heat a reaction if we want it to go faster. And sometimes we don't want the reaction that we want it necessarily to go faster, because maybe if it goes faster at the higher temperature, there will be some other reaction and therefore we don't get the product that we want. If you've come to any colloquy at all, you will have heard about that from the organic chemists, particularly Dr. McDonald, who thinks about this a lot. The idea that, sometimes he does reactions at very cold temperatures because the reactions that can occur with the product and some of the other things that are in the reaction vessel can be, not great for what he's trying to do. All right, so you can rearrange the Arrhenius equation to produce an expression that we can use if we know the rate constant at two different temperatures. So maybe at room temperature, we measure the rate constant. And at, 100 degrees C, we measure the rate constant. And we know already that whenever we're using temperature here, we've got to use Kelvin. So 100 degrees C would be 373.15 Kelvin. So we would want to use Kelvin in this case, absolute temperature scale. And we've been using Kelvin as our absolute temperature scale for a while. But this will allow us to take that rate constant measured at 2 different temperatures, all right, and use that to work backward and figure out what the activation energy would be. Okay, now we're going to see there's another form of this, but the other form is going to require us to make a plot, and I'm probably not going to have you make a plot, but I want to make you aware of it. So what does this look like? Well, it looks like a problem like this. So if we have NO2 reacting with carbon monoxide to produce NO plus carbon dioxide, so we essentially have an oxygen exchange here where one oxygen atom is moving from the nitrogen dioxide to the carbon monoxide. And we measure the rate constant at 2 different temperatures, 701 Kelvin and 895 Kelvin. Yeah, those temperatures are high. Some reactions have enormously high activation energies to make them go. And so we don't see them happen. And that's where, and that's that thing, and I can't emphasize it enough, the idea that, we've looked at a lot of chemical reactions, and you might look at them and be like, oh my gosh, it says like carbon plus oxygen to produce carbon dioxide or something, and you might say, well, you can actually buy a thing of carbon, like activated carbon or activated charcoal, and let it sit out. Why doesn't the reaction occur? And it all comes back to the activation energy is so high for some reactions. And so here, you have to heat it a lot to get to that activation, to get it to that activated complex, that activation energy. We have the 2 rate constant at 2 temperatures. So what I'm going to do is I'm actually going to cut to another video of me working this problem. I'm not going to work it right here. So you'll see when this video is finished, we'll cut, and then it'll be me working the problem, and then we'll go back to the rest of the lecture. We can also look at the Arrhenius equation in a completely different way. All right, so we can look at it as a single point instead of 2 separate points, where we can rearrange it and we get the natural log of the rate constant on the left, and we get this other stuff over here on the right, which, if you look at it, has the form of y equals mx plus b. So that means if we plot the natural log of the rate constant versus the inverse of the temperature, 1 over the temperature, we should get a straight line. And that straight line is going to have an intercept that's going to tell us, a y-intercept that's going to tell us about that frequency factor, that term A that we saw that told us something about the energy and orientation of collisions. So we could determine that. And from the slope is going to be the activation energy divided by the gas constant. So we can find the activation energy, we can find that collision, that frequency factor from an Arrhenius plot like this, where we've measured the rate constant at different temperatures, and then we do the natural log plot versus inverse in temperature, and the slope and the intercept will tell us something. So that gives us an idea of, how fast reaction rates occur. Now I want to talk about the idea of a catalyst, and I've brought up the idea of a catalyst before, where a catalyst is something that lowers the energy of that activated complex, of that transition state. And, it can do it in one swoop, or, there can be multiple smaller activation barriers that you have to overcome, but in general, what's going to happen is that activation energy is going to be lowered. And when you lower the activation energy, suddenly those collisions need to be productive, and the amount of energy that they need to get to reaction doesn't need to be nearly as high. So, we can get to that product state fairly easily, all right, or much more easily than we could before. So a reaction that maybe before needed to be heated to 250 degrees Celsius, or we can maybe do them at room temperature. So catalysts are incredibly important for helping us do a number of different chemical reactions. And we talked about the idea of a catalytic converter in the car that converts carbon monoxide to carbon dioxide. And that's something where there's a catalyst there. It's what we'd call a heterogeneous catalyst. The catalyst is a solid, and the molecules for the reaction are in the gas phase. So the gas phase molecules will adsorb, they'll sort of attach themselves to the solid surface until the reaction has been undergone, and then after the reaction's over, they desorb or detach from the surface, and they end up back in the gas phase. in reality, I mean, we would much rather have homogeneous catalysis where everything's in the same phase, but some things you can't do that way. There may not be a catalyst that exists that will do the particular reaction you want. So the catalyst effectively lowers the energy of the activation energy of this particular reaction. And so if we have a lower activation energy, we know the rate constant will be larger, and if the rate constant is larger, then the rate of the reaction will be larger. So that's great. We know that a catalyst lowers the activation energy for a reaction. All right. A great example of this is something that a number of you probably know about already. That's the idea of enzymes, or enzymes which are essentially protein catalysts, where we have a substrate. A substrate is the molecule that the enzyme or the protein is going to act upon, and it will bind to the enzyme, and so it will put sort of everything just right in the place that it needs to be. So if you think about that in terms of that collision, all right, in terms of the frequency factor and how the frequency factor played into the collisions, well, a protein in some ways, an enzyme, will direct the collisions in such a way that they'll be more productive more frequently. And so it's really, really, really cool stuff if you have a chance. I've actually done a lot of biochemistry through my undergraduate and graduate days, and in particular looking at enzymes and substrates and things like that. I just find it extraordinarily interesting. But that substrate will bind to that enzyme very specifically, so only certain things are going to fit. We always draw shapes, but and shape is part of it, but part of it is chemical functionality has to be correct for it to bind in that particular place, in that pocket, you'll sometimes hear it called. And when it does, it lowers, all right, it lowers the activation energy. You can see here there are sort of two activation bumps or humps in the enzyme substrate, or the enzyme catalyzed reaction. First one is normally due to there's some energy that requires getting that substrate into that place in that enzyme. And so once that's overcome, then the activation energy is significantly lower than it was before. It's easier to overcome. The reaction is faster. And so we get to products more quickly than we would have before. Really, really, really cool stuff. All right. Now, that's essentially it. That's all the more we're going to talk about catalysis. This is essentially the end of the kinetic stuff. And in fact, this is all I'm going to give you for this week. You just had your exam, these 2 lectures. That's enough. And from here, I'm not exactly sure where we're going to go. I mean, we could move further in this chapter, Chem 111, or I've got a couple interesting things that I wouldn't mind teaching you about, and they're actually related to chemical demonstrations. And then we could use those to springboard back into, I just absolutely love teaching redox. Electrochemistry is one of the things that comes up next. So maybe we'll detour into redox for a while and see then if we have time, we'll get into the electrochemistry part of it as well, because I actually am an electrochemist by practice, and so I have a different way of looking at electrochemistry than usually is presented in the textbook, and I think it's an easier way. You often think about how your professors, how you have a professor or a teacher that somehow motivated you, but mine comes back to the way that my research advisor in graduate school talked about electrochemistry. It just made all the sense in the world to me. But it's so incredibly different from the way that it's taught. And in fact, the way that some things are taught in textbooks about electrochemistry is just completely wrong. It ends up getting the right answer, but, doing something that gets you the right answer, but doing it for the wrong reason, isn't always the best thing, especially the further you get into science or medicine or whatever it is that you want to get into. You want to be doing it for the right reason, doing the right things to get the right answers. And so we may well get into that as well. But I also understand that you all have a lot on your plates from all your other classes too. So I don't want to be one of those professors or one of those classes where I'm pushing you so hard that you're actually doing significantly more outside of normal, teaching class times than what we were doing before when we were in the classroom. I get that you're having to do a lot more on your own, but I don't want to push you so hard that you're like, oh my gosh, we didn't do anywhere near this amount of work beforehand. So that's where we're going to go. I'll stop my rambling now. Have a great day.